aspirants, welcome to AgriVision for you. So with the GATE 2025 examination, it's the perfect time to boost your preparation by practicing more and more previous year question papers. So in today's video, we'll be walking through the GATE XE 2020 question paper covering the remaining 11 questions. So if you are new to our channel, make sure to subscribe and click the bell icon so you don't miss out our any latest examination tips and preparation strategies. Also, don't miss out our exclusive discounts for GATE 2025 batches. So click the link below for more details. So let's get started. Question number 12. Make the edible oil Match the edible oil refining stage in column 1 with its purpose in column 2. Okay. So first one is degumming. So degumming is the stage which involves the removal of phosphatides from the oil. Actually phosphatides, these are the compounds that can cause the oil to become cloudy or gummy. So P, it will go with 3, that is removal of phosphatides. Next next Q, neutralization. So this stage basically it involves the removal of free fatty acids from the oil. Actually free fatty acids, they can cause the oil to become rancid or they may have an unpleasant taste. So Q, it will go with 4, that is removal of free fatty acid. So bleaching, it is a stage which involves the removal of pigment from the oils. So pigments, it can give the oil a darker color or affects its flavor. So R, removal of pigments, that is winterization. So winterization, it is a stage which involves the separation of triglycerides that solidify at a low temperature. So this is done to prevent the oil from becoming cloudy when it is stored at a room cold temperature. So S, so my correct option will be D, P3Q4R2S1. Question 13. Match the root material in column 1 with its related term in column 2. So coffee. Coffee beans are primarily Arabica beans, which are a type of coffee plant. So P is 3. Cocoa. Cocoa beans, these are the seeds of the Theobroma tree, so which is a source of chocolate. So beer, it's the liquid which is obtained after brewing the grains. So which is used to make the beer is called the wort. So R, wort. And S, that is wine. So it is the unfermented juice of the grapes which is used to make the wines. It is must. Correct option will be B, that is P3Q4R1S2. Question 14. Match the component system in column 1 with the peeling method for fruits and vegetables in column 2. First is lye solution. So lye solution or the caustic solution. So it is P4. Actually this is the process of removing the peels of the fruits or the vegetables by immersion in a lye solution. So it is the oldest method which is used for the peeling of the potatoes or the tomatoes. Basically this involves the immersion of the material in hot caustic or lye solution. This can be NaOH or KOH at a temperature of 90 to 100 degree Celsius. These are immersed. So this solution, it dissolves the pectic or the hemicellulosic materials, we can say, material of the cell wall. Next is carborundum rollers. So carborundum rollers, it is for abrasion peelings. Basically the food is fed into this carborundum rollers they are placed into the rotating bowls which is lined with carborundums. So the abrasion surface, it removes the skin and it is washed away by a copious supply of the water. So it is Q3. Next, pressure vessel. So it is flash peeling. R1. It is actually, for examples, for root crops and all, these are fed into batches into a pressure vessel which is rotated at 4 to 6 rpm at a high pressure, and this is introduced, and all the food surfaces, these are exposed to the steams by this rotation of the vessels for predetermined time, and this differs according to the type of food. Next is the conveyor belt, that is S1, S2. Conveyor belts, basically, this flame peeling, it was developed for the onions. This peeler, it consists of the conveyor belt which carries and rotates the food through a furnace which is heated at around, we can say, 1000 degrees Celsius, basically for the onions. So the outer paper shells and the root hairs, they got burned, and the charred skins is removed by high pressure water sprays. So over here my correct option will be option number C, that is P4, Q3, R1 and S2. Question 15. Which among the given options correctly explain the nature of the microbial culture represented by the curves in 1, 2, 3 in the following figures? Options are germination of spores, homogeneous population and mixed population of spores and vegetative cells. So this is option A, option B, option C and option D. So we know that at constant temperature, the thermal death of the bacteria is exponential with the time. Over here, my correct option is option number B. Even this type of graph, they fall into four general types, actually, which was recognized in 1912. So over here, my curve A, that is line 1, it tells about the logarithmic death rate. That is, the survival curve is essentially logarithmic if the population of the bacteria is homogeneous with regards to the heat resistance. So this is homogeneous population. So line 2, it indicates the population as heterogeneous with regards to its heat resistance. So it is the mixed population of heat sensitive and heat resistant bacteria. And line 3 is about, it is similar to the curve A, but it tells wherein the tailing represents a small population of heat resistant cells. That is the germination. Means gradual decrease in the number of survivors over time. Means this pattern actually is consistent with the germination of spores. When the spores, they are exposed to heat, they germinate, they become vegetative cells which are more susceptible to heat inactivations. So this is germination of spores. So over here my correct option is B. Question 16. Match the equation or law in column 1 with its application in column 2. So first one is Planck's equation. We know Planck's equation of freezing. What is the formula? That is Tf equals to rho Lf by Tf minus Ti, A by Hc minus Ra square by K. Right? This is the Planck's equation of freezing. So my P, it will go with 2. Next, Arrhenius equation. So Arrhenius equation, so it is, this equation actually, it relates to the rate of constant of a chemical reaction to its activation energy and the temperature. So it is commonly used to study the temperature dependence of the reaction rate. So it will go with 3, activation energy. We know about its Arrhenius equation. Arrhenius equation is K equals to AE to the power minus EA by RT. These are the common equations. Next, Buhengium-Anderson-de Boer equation. So this equation basically it is used to describe the adsorption of gases on solid surfaces. Particularly we can say the monolayer adsorptions. Okay, so it helps to calculate the monolayer capacity of the solid adsorbent. So it is about the option number 4, that is monolayer moisture content, R4. So this GAB, actually these are most common models used in the determinations of the absorption isotherms for different materials. Okay. Next, as Stokes law. Stokes law, that is termination velocity. So basically it states that the force that retards a sphere moving through a viscous fluid, it is directly proportional to the velocity and the radius of the sphere and the viscosity of the fluid. So over here my correct option will be C, that is P2, Q3, R4 and S1. Question 17. Match the absorber used in modified atmospheric packaging and storage in column 1 with the scavengers in column 2. So first one is oxygen absorber. So oxygen absorber basically they rapidly attain and they maintain a zero oxygen in the modified atmospheric packaging, that is MAP. So this oxygen absorbers, they or the scavengers, they often need to remove the residual oxygens. So example of oxygen absorber is ferric oxide, iron powders or ascorbic acids. Okay. Next, carbon dioxide absorber. Function of carbon dioxide absorber is basically it is used in fermented products or packagings to maintain the packaging integrity. So over here my correct option will be magnesium oxide, Q. Basically this magnesium oxide, it is used to absorb carbon dioxide. So it reacts with the carbon dioxide and it forms magnesium carbonate. Therefore it removes excesses of carbon dioxide from the package. Next, ethylene absorber. So ethylene absorber, these are used to control the presence of ethylene, which causes ripening or senescence of fresh food and degradation of chlorophylls or leafy vegetables. So R is potassium permanganate. So this potassium permanganate is an effective ethylene absorber. It reacts with the ethylene or gas that can cause the fruit ripening and to form the ethylene oxides, and which is further decomposed. As moisture absorber, so moisture absorber, it controls the excess of moisture which is present in the food packages, which controls the bacterial growth or we can say mold growth. That is calcium chloride. So calcium chloride basically is a desiccant which is used to absorb moisture. So it reacts with the water vapor to form calcium chloride dihydrate, which helps to maintain a low humidity level within the package. So over here my correct option will be A, that is P3, Q2, R4 and S1. Question 18. During extrusion cooking, food materials are generally subjected to a combination of high shear, low pressure, high temperature, high shear, low shear, high temperature or low shear, low pressure. So shear, basically this refers to a mechanical force that causes a material to deform or break apart. So high shear would be beneficially for breaking down food particles, and low pressure might not be sufficient to force the food material through the extrusion die, especially if the material is thick or the viscous. So this option will be incorrect. Next, high temperature, high shear. So high temperature basically it is crucial for cooking the food, gelatinizing the starches and the inactivation of the enzymes. So it helps to soften the materials for easier extrusion. So this is correct. Next, high shear. With high shear, as mentioned earlier, like high shear is beneficial for breaking down the food particles. So it creates a uniform mixture. So this option is correct. That is high temperature, high shear. Next, low shear, high temperature. So low shear might not be sufficient to break down the food particles effectively, which leads to the less uniform product. And high temperature, so high temperature is, we know, it's still beneficial for cooking, gelatinizations and all this. So without sufficient shear, the food might not be properly processed. So this option is also incorrect. Next, low shear, low pressure. Low shear means it's not ideal for breaking down the food particles. Low pressure, it would be difficult to force the food material through the extrusion line. This is incorrect. So over here my correct option is high shear, high temperature, high shear. So the combination of this high temperature, high shear, this is most effective for extrusion cooking, since the high temperature ensures proper cooking, gelatinization, while the high shear, it breaks down the food particles, it creates a uniform mixture. So this combination is essential for producing high quality extruded products. Question number 19. The whole milk at 22 degrees Celsius is pumped through a steel pipe at a flow rate of 3 liters per second. So volumetric flow rate is 3 liters per second, or it can be written as 0.003 meter cube per second. The length and the inner diameter of the pipe are 40 meter and 4 centimeter. So length L equals to 40 meter and inner dia, that is 4 centimeter. The viscosity and density of the milk at the temperature is 0.2 Pascal second and 1032 kg per meter cube. So viscosity, it is 0.2 Pascal second and density, it is 1032 kg per meter cube. These are the data given. Now first we have to calculate the area, is the cross sectional area of the pipe. So A equals to pi r square. Pi, we know, 3.14 into d by 2, which is equals to 3.14 into 0.04 by 2, or it is 0.02. 3.14 into 0.02, so we'll get somewhat 1.25664 into 10 to the power minus 3 meters square. This is my area. Next we have to calculate the velocity of the fluid. So how we'll calculate the velocity? First area. So we know volumetric velocity equals to volumetric flow rate equals to V into A, or we'll calculate V equals to volumetric flow rate by A. So volumetric flow rate is 0.003. Area we have calculated 1.25664 into 10 to the power minus 3. So it is 2.3. Now we have to calculate the Reynolds number. Since we have got all the data, we know Reynolds number RE equals to rho into characteristic length by V. So density is 1032, velocity is 2.3, 386. L is 0.04 by 0.2, or we'll get 493.23, approx 493. So the Reynolds number is 493. Question 20. A hammer mill operating at a feed rate of 108 ton per hour consumes 10 kilowatt power. So feed rate is 108 ton per hour. Consumes power. Power consumption is for reducing size of the wheat grain from 3.92 to 1.25. So DP product will be 1.25 mm and feed is 3.92 mm. If the Bond's law, so we have to calculate the Bond's law, holds good, the feed rate for reducing the size of the wheat grain 0.75 mm at the same power consumption level will be how much? So let this be my case 1. So case 2, feed rate we have to calculate. This is how much? Power consumption is same, that is 10 kilowatt. DP, it is 0.75 mm and DF is 3.92. This will be my case 2. So according to Bond's law, the formula P by F equals to 0.3162 the I by 1 by root over dp minus 1 by root over df. So for case 1 is 10, f is 108, which is equals to 0.3162 omega I by 1 by root over 1.25 is root over 3.92. So let this be my question 1. For case 2, 10 by f we have to calculate. So 0.3162 omega I by 1 by root over 0.75 minus 1 by root over 3.92. Like question 2. So just we have to divide 1 by 2. So we have to divide equation 1 by 2. So what we'll get? 10 by 108 by 10 by f. So this gets cancelled, which is equals to 0.39 by 0.65. 08 or f equals to, this we'll have to first calculate. This is 0.6. So just put the value, we'll get 6.48. So f, the feed rate will be 64.8. 21. During spray drying of a milk sample, inlet and outlet temperatures are maintained at 132 degrees Celsius and 80 degrees Celsius respectively. So T1 132 degrees Celsius, T2 80 degrees Celsius. If the ambient temperature is 29 degrees Celsius, so T0 is 29 degrees Celsius. Thermal efficiency of the dryer will be how much? So heat efficiency. So heat efficiency is T1 minus T2 by T1 minus T0. Just calculate 132 minus 80 by 132 minus 29. So it is 50.48%. So this will be my answer. Question 22. An orange juice flowing at 0.80 kg enters a counter current double pipe heat exchanger at 20 degrees Celsius and leaves at 72 degrees Celsius. So mass flow rate M is 0.80 kg per second. Inlet temperature, that is T in, is 20 degrees Celsius. T out is 72 degrees Celsius. Now inlet outlet temperature of hot water used as a heating medium in the exchanger are 81 degrees Celsius and 74 degrees Celsius respectively. So T for hot in is 81 degrees Celsius and T for hot out is 74 degrees Celsius. So this is for hot water as a heating medium. Now specific heat of the orange juice is 3.74 kilojoule kg Kelvin. Okay, specific heat means CP is 3.74 kilojoule per kg Kelvin. And overall heat transfer coefficient is 492. That means U is 492 watt per meter square Kelvin. Now we need to first calculate the heat transfer surface area, that means A. So to calculate the heat transferred, we know that heat gained by the orange juice, we can calculate from here, that is Q is equals to mass flow rate, specific heat, delta T, that is out by in for orange juice. So mass flow rate is 0.80, Cp is 3.74, out is 72 minus 20 degree Celsius. Okay, calculating this, we will get Q equals to 155 joule per second. We just convert it kilowatt. It is 155.552 kilowatt. Now we have to calculate the LMTD, that is log mean temperature difference. LMTD. So del T1 is hot in minus out for the orange juice, that is 81 degree Celsius minus 72 degree Celsius. It is 9 degrees Celsius. Delta 2, that is hot out minus in, that is 74 degrees Celsius minus 20 degree. It is 54 degrees Celsius. Now LMTD, that is delta Tm, delta T1 minus delta T2 by ln del T1 by del T2. Just put the values. 54 minus 9 by ln 54 by 9, that is 45 by ln 6, it is 45 by 1.79176, that is approx 25.12 degree Celsius. Now we have to calculate A over here. We know that Q, that is using the heat transfer equation, Q is UA delta T. So here we'll get A. So A equals to Q by U A del Tm. Q we have calculated 155.552 kilowatt. U is 492. Delta T, that is 25.12. So we'll just put the values. So the final answer, that means the heat transfer surface area, is approximately 12.58 meter square. 12.58. So with this we have completed GATE XC 2020 question paper. Hope you liked the video. So till then, thank you and enjoy learning.